Okay, so hello everyone. So today we are going to discuss this OTOCs in holography, and this is going to be the final part of the series of discussions that we have had on this topic so far. In the previous discussion, we dealt with the purely boundary picture of OTOCs, like we discussed this physical intuition of vanishing of OTOCs for chaotic systems, and then we took a rather detailed detour into Penrose diagrams, and all of that discussion in the previous part would help in this final discussion as well. So, as I discussed in the previous part, that there would be broadly 4 topics that I'm going to cover, like 4 sections that I'm going to cover in this discussion. So we are done with the first two parts, namely the physical intuition of OTOCs, and second the Penrose diagrams. Now we want to see the physical intuition for the corresponding holographic picture in a third part, and then finally in the concluding part we'll have this detailed discussion on the procedure, like all the mathematical procedure of exactly computing the Shockwave profile. Okay, so I'll start off with holographic picture. The discussion on Penrose diagrams would be really handy, and also of course the discussion on the purely boundary picture also will be very important to understand this. So okay, yeah. So if you recall, in the previous part, I had these 2 states that I've written down, which were minus t of x0 and some thermal state beta, and the second state that I had was v of x comma 0 omega 0 minus t acting on this thermal state beta. So these were the 2 states that we talked about, and we talked about what's the physical difference between these 2 states, and how the inner product of these 2 states gives us what we call as the OTOC. Okay, so in the previous part we saw that like what's the precise picture in the boundary. Now when we are doing dealing with these 2 states in the boundary, what's exactly happening in the bulk? That's the goal of this section. And so to go into the holographic picture, firstly it's key to note that every operator, let's say V in the boundary, has a corresponding scalar field associated with it in the bulk. So this is a dictionary. This comes from ADA-CFT. So okay, basically the approach that I will take here would be the approach of what we call as the 2-sided geometry. So we also had this discussion of thermophile double state somewhat in the first part. I'll make that clear exactly why do we need that thermophile double state, and as Overs had mentioned in those earlier parts, it indeed in the like purely quantum information theoretic picture, it has to do with that purification thing that he was mentioning. Okay, so this is a key thing to note. So what happens is, suppose this is my boundary, and oh, okay, maybe let's just draw the Penrose diagram itself. Okay, so this is my Penrose diagram. Which I had discussed in detail in the previous part. But in the previous part, I had constantly kept mentioning this thing that like the thing that we arrive, like the procedure that we used to arrive at this was gluing various Penrose diagrams, and I claimed that even if we do the Kruskal extension or the Kruskal coordinate transformation of a given metric, in those coordinates also we get this globally extended picture of the space-time. Okay, and I had mentioned like why this is a maximal extension. These curly lines is of course a singularity. So this is a past interior, this is a future interior, this is the left exterior, this is the right exterior. I discussed these 4 parts of the Penrose diagram, and in our subsequent discussion of the fourth section, we will be dealing with the Kruskal transformation, like the Kruskal coordinates of the given metric, and it is very necessary, as we will see. Like it very nicely fits the physical picture for this OTOCs. So what happens is, suppose, okay, one more thing to remember, I'm taking the time orientability of my Penrose diagram in the upward direction. So that's increasing time in the upward direction. So suppose at certain time, let's say 0, okay, at some position, I act with an operator on my boundary. Okay, so these are the 2 boundaries. Okay, so we had discussed this, like we have 2 black holes, they are connected by a wormhole. That's exactly what this picture is showing. So that's why we call this as a 2-sided geometry. 2-sided because now we have 2 black holes connected by this wormhole. Wormhole is precisely this point here in this Penrose diagram. Okay, so suppose I act with an operator V in the boundary. So as I said, every operator in the boundary has a corresponding scalar field or the scalar perturbation in the bulk. So in the 2-sided geometry, the holographic picture is, when I act with this operator, what happens is, I have a particle that emerges out of the past interior or the perturbation. It reaches this point at t equal to 0, and then it falls into the towards the future part. Okay, so like if we were just merely dealing with a single like one-sided geometry, this picture would have been, we wouldn't have like this past interior, like a particle coming from the past interior part. We only would have said, okay, as we give a perturbation here, there will be a scalar field phi that will propagate towards the black hole. But in the 2-sided picture, it is coming from the past interior, so it's coming from another black hole, and it is getting into the exterior of the other black hole, it reaching the boundary at this time, and then propagating towards the future interior. So this is what the holographic picture is in the 2-sided geometry. And so like this is one boundary, this is one boundary, so we have a one black hole, in that one black hole we have one boundary, this is a second boundary for corresponding to the second black hole. So when we were writing this thermofield state down, we were saying, okay, it goes like some tensor product of the eigenstates of the left boundary times eigenstates of the right boundary. So this is what we mean. So left boundary corresponds to this, right boundary corresponds to this. So in the two-sided geometric picture, we necessarily this thermal state beta is necessarily a thermofield double state. Okay.
Particles coming out of the black hole.
Yeah, this is from the past interior of the other black hole, and getting into the exterior of the other black hole. It's not the same black hole. Like it's not like it's coming out of the same black hole and getting into the exterior of the same black hole.
From a different black hole. It's
Yeah.
coming out.
Yeah.
Like a Hawking radiation sign.
No. It's not Hawking radiation. It's just like it is allowed. I discussed in the previous part, right? When I draw these causal curves, like it is a time-like curve. This is perfectly allowed curve, right?
Okay.
So this is possible. Okay, so this is the picture. Now I will elaborate. Use my space judiciously. Try to do everything here. Okay. So now the entire idea was that suppose I act with an operator V at time 0 and let's say position X, this operator. Then we said, okay, like if the system is chaotic, we said that we would back evolve, act with the operator W, and then again forward evolve. That this state would have a very small inner product with this state in the case of chaotic system. I discussed this in detail in the previous part. So let's consider what's happening in the bulk then. So if I again draw my Penrose diagram. And by the way, in these crucial coordinates, that the diagonals that I've drawn, which are these light-like directions, they we'll have these coordinates u comma v. These coordinates are precisely these two light-like directions. So the convention that I'll use is I'll use this direction as v and this direction as u in the crucial coordinates. This is what it's going to be. Okay, so. Now suppose what is happening, like if I consider this first state, so in, what should have happened, at when I, if I do not consider the perturbation just as yet, what should happen if I act my operator at the position x at time equal to 0, there should be a particle that should emerge from the past interior and then fall into it. Now if I bring this W into the picture, what will happen is, suppose I act my operator W at some past time, that's why I've written minus t. So suppose I act my operator W at the origin at time minus t in the past. So what will happen is, the particle again will emerge from the past interior, reach W at 0. It happens for any operator, right? This dictionary holds true for any operator. So the particle comes here, I have my W, and then it starts falling again, like towards the horizon. Now what happens is, now if I act my operator W at a sufficiently large time, in the consequent discussion, it will be very clear what sufficient means. What happens is, when this particle starts to fall towards the horizon, its energy gets exponentially blue shifted. Okay, so when we are drawing this picture, when this particle goes through the horizon, the energy from the perspective of now the thing is, we are using these past notions. So I'm using my operator at minus t. So at the time I will do my measurement, that I'm fixing as okay, that will be my time equal to 0. So I'm not varying my time in the future, I'm just varying my past time, right? It's totally equivalent to do that. So this energy, when this it gets exponentially increased, so T is the time, and beta is the Hawking temperature of the black hole. The inverse Hawking temperature of the black hole. So as as the energy of this particle, as it propagates towards the horizon, as this energy increases, the more and more the energy increases, it becomes sufficient enough now that it starts affecting the space-time. Okay, so now this acts like a significant perturbation in my space-time, right? And this is not a metric perturbation. This is like coming from like the tensor. My energy content of the space-time is changing, so there will be a perturbation in my stress tensor because of this exponential shift. Sorry, exponential increase. So what will happen is, as this perturbation travels towards the horizon, so here is my perturbation at some time. Then because of this exponential shift in this v direction, what will happen is this, suppose my perturbation is this, it will get very much stretched in the v direction, and it will get suppressed in the u direction, right? So when it gets near and near to the horizon, what will happen is it will create a localized shock along the horizon. Like it will become a like flat. So if I represent that with 2, so there will be a shock, like a localized shock across this, which will, like with time, what is happening is this perturbation, as I said, because of this exponential behavior, it is getting stretched in the v direction and compressed in the u direction. So like this green line, for sufficiently large times, sufficient again will become very clear. Sufficiently large time, what will happen is that it will keep getting stretched in u, in v, and suppressed in u. So what will happen is this green perturbation will now very locally get spread over this horizon, which I have now represented with a blue line. This is precisely what we call as a shock wave. Shock wave which is localized at this horizon. Okay.
It's because of the particle.
Yeah, because like the particle keeps gaining energy and yeah. Okay, so now I have a significant effect in my stress tensor, and so the effect of this shock. No, I think we are dealing with this, right? So the shock would have been on the other line.
That's true.
So like this is the first black hole, right? So the perturbation is traveling in this exterior. So the shock should have been along this V. I drew the wrong one.
Which is the first black hole?
Yeah, this is the first black hole. This is the second one.
Okay.
Yeah. So the shock should have been on this one. Now I have a shock. Now the presence of this localized shock along this horizon will change the physics, right? So this was the operation of my perturbation operator W in the past time t. Now what happens is, like without this operator W, what should have ideally happened is particle should have emerged from here. I should have reached t equal to 0 at the boundary, and then again go into the future interior. But now what will happen is, like the effect of the shock will be what, so when the particle starts emerging, like it has to reach at time equal to 0 to produce V, right? So now what happens is, now it encounters the shock, right? So now the effect of the shock is that now its trajectory gets shifted. So if I lot of colors today, its trajectory now gets shifted. So if I would have said, okay, now this operator W like wouldn't have acted at a sufficiently earlier time, what would have happened is this perturbation would not have reached the horizon, and there wouldn't have been any localized shock, and this particle would have happily just crossed this past interior and would have reached at t equal to 0. So this sufficiently larger time that again and again that we are saying is very important. Okay. So the effect of the shock is that its trajectory now gets shifted, and now because of this shifting, the particle will not reach at time equal to 0. There will be some time delay. Right, time delay, because in the Penrose diagram I said the time increases in the upward direction. So now this shift would ensure now that the particle would have to leave from here, and then it will reach at some later time and not t equal to 0. Okay. So this state, this was the picture that I was giving, the holographic picture for this state. The second state is that I don't care about V first. I just say, okay, now I first create my shock, and then I prepare my system such that the particle will face the shock. After the shift, whatever the shift, we account for the shift, and after that shift it reaches at t equal to 0 at this V. So that's the difference between these two states. Now because of this perturbation operator in this state affecting the time at which the particle is reaching at the boundary, and now the overlap between these two states starts to decrease, because this state means that exactly at t equal to 0 my particle is getting formed, right? But this state, but like when we get this operator, the perturbation operator in the past, what this means is that now my operator V is failing to rematerialize at that time t equal to 0. So now the overlap between these two states starts to decrease, because these are two different states, right? So now suppose we wait for more and more time, right? So the strength of the shock will keep increasing, right? Because this is an exponential behavior. So the more time we keep waiting, the strength of the shock increases, and what happens is that the strength, the amount of shift that this particle suffers due to the shock will keep increasing, right? So suppose at some other time the shift would be this much, and the particle would again reach very late. Then there would be some time when this shift becomes so much. Now suppose the shift has become this much in strength. Now the particle has got into the future interior. Now it cannot escape. Right? As soon as the shift becomes so strong that so wide that now the particle gets trapped into this future interior, and from the future interior we know it cannot escape back to the boundary. Right? So it comes after this special time, like when the shift becomes so significant, V fails to materialize at all. Like previously it was okay, some delay, but at least it was appearing in the boundary. Now there is no V at all. So this overlap will totally vanish. And this time exactly is what we scrambling time. Yes.
Okay, scrambling time is that time in the bulk.
Yeah. Scrambling time, or depending on this position x, time something of the order of t star. Like if you recall the last discussion, I said t star is a time when at the position which we are acting this operator, at that time that particular position is getting scrambled. After that time, the local degrees of freedom start to get scrambled. So like if this x that we are saying, that which is spatially separated, if it's just in the neighborhood of 0, like precisely just greater than t star, this particle will go into the future interior. Right? So this time, that the special time that I'm talking about, is t greater than or of the magnitude t star. Okay. So this is the holographic picture. Right? So like overlap of course is OTOCs, right? That I discussed. So what this means is that as this shock increases, it directly affects this overlap, right?
Yeah.
So physically, what one can expect, that this overlap OTOC is directly related to this shift. Right? And indeed, when we solve this, we will see, like we have discussed, that OTOC from the boundary perspective takes this form of exponential e to the power lambda t minus t star and minus x by vp. We'll solve for this shift, which I'll call as neta of x comma t. This shift that we'll find, we'll see that the behavior of this OTOC and this shift is exactly similar. Okay, and which is clear now from the physical picture, that indeed should be like the more the shift, the more that there will be vanishing, right?
Yeah.
And we said that in this chaotic systems, this OTOC vanishes. So that's the holographic picture. Okay, so in the previous section we saw the precise holographic picture of what goes on, like why OTOCs is related to this shift that we indeed call as a shockwave profile. And now let's venture into the final part of this discussion of OTOCs in holography, and that is explicit procedure of, so like explicit procedure of computing this shockwave profile. And thereby VV. We'll see exactly how VV follows. Okay, so this is the final section of this discussion. So I will divide the board into two parts. So mathematical. Okay, so so firstly, suppose that I have a metric of this form. Let's say G of Z, H of Z, T square, G of Z, F of Z, dz square, K of Z, dx. Okay, so suppose this is the most general form of the metric that we have. And where this dxi part is planar and isotropic, meaning when I say that this kz, so suppose this is dx1, like there is no, like this part is flat, right? So like, suppose if it is not flat, there would be like other coefficients that would appear, and that would like basically what I want is, I want this kz to be a common factor multiplying this part. If this is non-planar, like the metric will pick up another term, and the individual functions that I multiply, suppose there will be terms like this, right? dx1, dx2, and on. So there will be a coefficient for this term, right? So if this is not a flat part, along with k of z, with there will be some other form, that's maybe r square times k of z, and then it would not, like in that case my analysis won't work, right? So I particularly want this form, and I also want isotropy. Again, if it's not isotropic, I again have some function and that it will multiply to, and then it will break my analysis. So I want planar and isotropy. Okay, so this is the general form of the metric, and the three models that we are going to analyze in our work also follow exactly this form with different values for kz and different expressions for k of z, f of z, g of z. And g of z is the blackening function. So to this metric, I can do my Kruskal coordinate transformation, which is e to the power 2 pi by beta r star minus t, and v is going to be minus e to the power 2 pi by beta r star plus t. So where this r star is my tortoise coordinate, and when I do this Kruskal transformation, this is exactly what, this is a explicit form of the Kruskal transformation. I get my metric in the following form, which is okay. So this is the form that I get, where A mu mu and B of UV, sorry, not mu mu, A of UV and B of UV would be the function of these various functions that I have in my original coordinates. So these functions A and B are totally geometry dependent, model dependent, like with the model and geometry we are working with. Okay, so this is what we call as a Kruskal form. In these coordinates, we are going to get the Penrose diagrams that I just drew in the previous section, and also in the previous discussion. Okay, so yeah, so once I have this is my metric, and in these coordinates, if I write down my stress tensor, the unperturbed stress tensor, this 0 represents the unperturbed one. This before I have brought in my W operator and brought in any perturbation, and it takes the following form. Okay, so this is the unperturbed stress tensor in these Kruskal coordinates. Now I said that now I will be for sufficiently large times, what will happen is that there will be a localized shock along one of my horizons. So like if I again draw the Penrose diagram just for reference. So if I can, I'll use this convention. I'll use this direction as V and this direction as U. Like since this direction is V, so this line also corresponds to U equal to 0. And since this line is U, this line corresponds to V equal to 0. Okay. Yeah, so I have my initial metric, the unperturbed stress tensor. Now, when I bring in this shock, like when I wait for sufficient time and I have a shock along my local horizon, the perturbed part of the stress tensor, which comes due to the shock, so I will represent it as shock. Now, I said that it will come along this line, right? This is where my shock will be. Yeah, shock. Okay. So this is the shock that I get, and I said that this will be totally localized along this horizon, and the equation of this horizon is U. So the perturbed part of the stress tensor will only have like UU component, and like this would be very obvious, like what form this will take. Right? So I said this shock it will come due to this energy part that I have written, which grows exponentially. So this is my E naught, the energy that the perturbation started with at the boundary, and then it kept exponentially growing. This energy times del of U. Why del of U? Because my shock is localized along this horizon, U equal to 0, and then some generic function A of x. Okay, and this will depend on the type of perturbation that we are applying. Okay, so this is my perturbed part, right? Due to the shock, the stress, the component that comes into the stress tensor, and Also what happens is, like, if we look at this Penrose diagram, uh, I was consistently saying that because of this shock there will be a shift in the coordinate, right? And in this direction I have taken V. So after the shock, let's say my coordinates get converted into U bar, V bar, right? So my V bar would be my initial V plus Heaviside step function of U times this profile that I was calling the Shockwave profile. Okay, so like this part is clear, right? This function I was defining as a shift because of this shock wave. Now this part is to ensure, like, this Heaviside step function everyone knows, right? When I write this Heaviside function of U, this means for U less than 0, this is going to give me 0, and for U greater than 0, it's going to give me 1. Right? So that's how we define this Heaviside function. And why I've taken this is due to the shift, right? And until and unless the particle comes at this horizon V, horizon U equal to 0, or this V direction, it is not going to experience anything, right? So all like my causal properties do not change on this side, right? Once the particle from this side comes to this and then gets shifted, then its causal properties change, right? So this is the direction of my increasing U, right? So this is U equal to 0. This is U less than 0. This is U greater than 0. So for U less than 0, there is going to be no shift, because it still hasn't encountered that shock along the horizon, right? So this will just give me V bar equal to V. But as we go beyond, like U greater than 0, this will become 1, which will give me some shift. Okay. Right? So I hope it's clear, like, why the Heaviside function. Okay. And then of course the other coordinates will remain unchanged, because there is no encountering of shock along those. And X bar equal to X. Okay. And now basically after perturbation I have my stress tensor, like the perturbed part of the stress tensor. The total is of course going to be the unperturbed plus the shock part. Okay, I will not get into that. We'll go slow. So this is, I think everyone agrees now, this is how the coordinates will change. Now with these change coordinates, how will my metric change? Of course my metric now in terms of V bar, U bar and X bar is going to look something different, right? So the only part that is changing is this. So I have my dV here, right? So I have to substitute dV, something for dV, because du bar is simply du from here, dx bar is simply dx from here. dV is going to be different, so I'll find that. So I hope everyone agrees that dV bar is going to be this. Agree? I've just differentiate, and the differentiation of this Heaviside function is my direct help. Okay. So I have this. When I substitute back here and replace my U with U bar, V bar, X bar, this is the metric that I get. This becomes 2A of U bar, V bar, du bar, dV bar, plus du bar, V bar, dx square, minus 2A U bar, V bar, del of U bar, this function nxt, and this should be du, so du square or du bar square. So wherever I have du, I directly replaced with du bar and u with u bar, right? So due to the shock, my revised metric is this now. The extra perturbed part is this. In these coordinates, of course, my initial unperturbed tensor will also gain a new form now in these new coordinates, and the form that it gains is pretty lengthy. So I'm not sure if I should write that down. Should I?
No, it's okay. You can skip.
It's a simple procedure. Like whatever you have, you know the transformation. You just have to plug it back here, and you'll get this like initial unperturbed part in these coordinates. Okay. Okay. Now all the ingredients are ready. Now our goal is to find out this shift function or the Shockwave profile that we are calculating. We physically did claim that this Shockwave profile is going to exactly be related to my OTOC. We saw that physically, and now we'll see that via mathematics as well. So once I have all my ingredients, I have the metric, I have my stress tensor. By the way, the stress tensor would be the unperturbed part, which I had initially, plus the part that is coming due to shock. So this is my total stress tensor. Okay. So I'll just represent it by T or T mu. So of course now I have to solve for this neta. Neta will take a specific form because these metric and the stress tensor are related by the famous Einstein equations, right? So my Einstein stress tensor is going to be my 8 pi Gn times this T matter plus this T shock. Okay, so when I like this part, this Einstein tensor, I can completely get from this metric, because this is a geometry part, this is a matter and energy part. So I will compute all the curvature tensors and everything. I'll get this. I already have my T mu shock there and T mu matter in these mu bar v bar coordinates that I haven't written down, but one can simply follow from there. So when we solve for the UU component of this equation, you do not have to solve for all, because like if you look at the metric, right, all the interesting information is this in this UU part, because here lies my the Shockwave profile, right? So I just have to worry about the UU component of this equation, and it turns out to be following. By the way, now you will see that I have everything in my bar coordinates, and then I suddenly switch to UV. It's nothing, it's just again renaming. We can do that, like these are just coordinates. I just don't want to see bar again in my. This does not mean that this UNV is exactly the UNV that we had initially. It's just that I'm now don't want these bars anymore, so I just am replacing those bars with UNV, right? It does not mean I have captured all the information already, so I do not need to keep the bars. Okay, so this is the equation that I get. Now this might look a complicated differential equation. I need to solve for this neta. It might look a complicated equation, but note that we only have to solve along that horizon, right? So in this equation, wherever I have this, okay, I have my del u del v of b, I will evaluate this at v equal to 0. Oh, sorry, yeah, u equal to 0, because I am near the horizon, right? So all my quantities that I have, right, this, the A of UV, B of UV, all at the horizon. Okay, so when I do that, I'm just going to write the final solution now. So this is what my Shockwave profile turns out to be. it takes the following form, barring a factor. So 2 pi by beta t minus t star minus beta m by 2 pi x. And this we should be happy looking at this.
Yeah.
Because I did claim just on physical arguments that my Shockwave profile is directly related to OTOC, and I just simply solve my Einstein equations in the bulk, and I precisely get my the Shockwave profile, which looks very much like my like the corresponding OTOC expression, where T star is this factor I've just written here. So I'll write down what this T star is. I also have this extra mu here, so I'll just m, which I'll define. Okay, so this is my T star, and my m is square root of b minus 1 by 2 b prime at 0 divided by this is my a of 0 divided by b prime of 0. Okay, so I do nothing. I said that I will compute everything at my origin, that is my u equal to 0, and then I just redefine these quantities, like give a new variable, right? So I can see a of 0 divided by b of 0 and everything, and I want to put it into the exponential along with this part. So I've just defined my T star in this way. Like if you put like instead of T star all these parameters, you're exactly going to get back above. I've just given names to these.
A naught is A of 0, right?
Sorry?
ln A naught.
Yeah. A naught is A evaluated at the horizon, B evaluated the horizon, A again evaluated horizon, B prime is this thing. Del U, del B, B and horizon. Okay. Now it takes exactly the form of the OTOC. If you remember the commutator, either way, because both are just related to each other. So we had this a lambda L T minus T star minus
same exactly. Almost same.
Mod x by VB. So now I can just read off my Laplace exponent is 2 pi t, maximally chaotic. T star I just already defined, and my VB is now precisely 2 pi by beta and this m that I've written here.
But we just need m.
Yeah, we just need m. And m comes from, we start from the geometry, we do this critical transformation, we arrive at this, and then we simply have to find a0, b prime 0. It's not like very straightforward. Of course, when one computes this, there will be 0 by 0 forms, and we have to take limits and all. So, but as soon as we get to this step, everything else follows generically for all the models. Once now I have my expression for the butterfly velocity, which is 2 pi by beta m. I can just you do the Kruskal transformation, find these by doing non-trivial calculations, substitute here, and I have the butterfly velocity for my model.
And lambda L is 2 pi b.
Lambda L is 2 pi by 2 pi t, and my scrambling time is what I've defined.
Okay.
So yeah, that's basically it.
So let's give a round about applause to